All right, in today's lesson, we are going to be exploring how to get the regression equation for exponential models. So we are going to be looking at data that models an exponential function, and we are going to be determining the exponential regression equation. So very similar to what we did with polynomials with the quadratics and the cubic model, except that we'll be dealing with exponential models. So just a quick recap. Here on Desmos, I've plugged in our basic exponential model, y equals a times b to the power of x, where a is the initial value, or the y-intercept. It also represents the coefficient, and b is the rate of change, where if b is greater than 1, then it is exponential growth, as you can see here. And if b is between 0 and 1, then it's exponential decay and the value goes down. Note that x is in the exponent position. Okay, so if we're dealing with exponential regression models, we need to look at what it looks like. So if you refer to the notes, the function regression models on Desmos, that handout you guys should have, if you look at the exponential row, then you will see what it looks like. So the exponential regression model for Desmos is y1 tilde a times b to the power of x1. Notice there's still y1 and x1, and x is in the exponent position. So this is what we'll be typing into Desmos in order to get our regression model. Okay, so if we refer, close that off. If we refer then to our note set, you had the note set from Monday, and then the note set I asked you to download today from the Microsoft Teams site. You should have the characteristic of exponential functions. And so if you want to turn to the page that says modeling data using exponential functions, that's what we're going to be looking at today. As well, the note set here, exponential regressions without a data table. We're going to be looking at that as well. So there's two scenarios. Scenario one, you're given some data and you're going to determine the model. And the second scenario is when you are not going to be given a data table. You're going to be given a scenario and a context, and you're going to have to then build the data table. And there's some different methods that we are going to be looking at. So two different things that we have to do. So the first one we're going to do is looking at how to build an exponential regression model when we have data given to us. So here we have some data. We have the year 1900 is year 0, and the population is in millions. So the table on the right displays Canada's population from 1900 to 2000 in 10-year increments. So N here would represent the years after 1900. So if it was down at 70, that would be the year 1970. So we want to determine the model. So again, our table, the year is here. I'll put this in red. The year is going to be our X, and our population is going to be our Y. Okay, so we're going to plug this data into Desmos. So I'm just going to minimize this, make that smaller, and we can plug this in here. So it goes 0 to 100 for the X. So we have to input a table. So 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. It's a lot of data, but that's fine. That's what we're given. Now we can input the Y values. So we have 5.4, 7.19. So 5.4, 7.19. We have 8.79, 10.36. 11.49 and then 14. 18.22, 21.55. One. Then we have 24.33. And the last two data points, 27.28 and 30. Make sure you've typed in your data properly and check. Okay, so we should have a scatter plot. We don't see anything, of course, because our window is off. So we're going to go into our graph settings. So our largest, so our X should go from 0 to 100. We'll probably make it go a bit further than that. So we'll go X-axis, we'll say to 150. And the Y-axis, we'll take it to 50, just to go beyond 30. Okay, there we go. Now we clearly can see this scatter plot. We should label the X-axis. The X-axis is years after 1900, and the Y-axis is population, and that's in millions. Make sure that that is properly labeled, and we are good to go. So we have our data table here. Sorry, our data table there, and we have our scatter plot there. So it kind of looks exponential. It's not perfect. Again, this is real life data, so nothing is exactly perfect. However, we will go ahead and do the regression model. So the regression model, as you remember, if you look on the handout for the Desmos regression equations, y1 tilde ab, so that's a times b, and then we would go a to the b, so to the power of x1. Make sure x1 is in the exponent. Now you'll notice right away that there's an option called log mode. It's very important that we click that. Now the reason why we click the log mode is because the log mode basically matches the algorithm that Desmos uses to the algorithm used by the Texas Instruments calculators. So it kind of matches what the graphing calculators would give. So we're just going to click that, and I'll just scroll this down. So right now you see the R-squared value is 0.9837. Certainly not a perfect model, but that's the data that it's based on the data that we're given. We have the A value is 6.6 and the B value is 1.05181. Now if we click log mode, okay, it increases the R-squared a little bit and it changes the A and the B. So just to be consistent, please make sure that when you are doing a regression equation problem in Desmos that you always click log mode. Okay, so we have our data, okay, and we have our regression equation. So in here, we'll just maximize that again. I'm gonna delete that because we're doing it in Desmos. We're gonna input what we need to do. So it says to construct a scatter plot and the curve of best fit. So I'm going to go to Windows Snip, and we'll snip the graph. So make sure that we get the labels good, copy and paste. Make that a bit smaller, doesn't need to be that big, and make that left justified. Okay, so we have our graph. Determine the exponential model that fits the situation. So I'm going to go back to Desmos and I'm going to snip this information here because that represents what the model is going to be. So we'll do a new snip. Let's put that down. Do that, and we'll paste it into our note set. A bit smaller there, so it fits on one page. Okay, we'll paste that and make that a bit smaller. Okay, so just to save space, I'll do a text box. Okay, so I'll do it right here, and we'll do this in red. Okay, so our model is y1 bigger. y1 tilde a times b to the power of x1. Now, we don't have a context of variables. We said that x is the year and y is the population. Again, if it's going to be different letters, variable letters, then you do make sure in the model that you have those letters. Okay, so the a value is 5.98354, and the b value is 1.01732. Okay, so now to put this, to get our equation, we would go y equals, again, we take away the tilde, so y equals a. Now we're going to take it to 2 decimal places. So 5.98. And we want the b value to 2 decimal places. Okay, so the y value is going to be 5.98 because, of course, it is the 8 is followed by a 3. So 5.98 times bracket. The 1.01, the 1 rounds up to 2, so 1.02, and then to the power of x. And that would be our exponential regression model that best fits the situation. So I'll plug that, delete that, and paste that and make it a bit bigger. Okay. So that is our model, and we have gotten the equation. So I kind of did the work here, the equation. Okay, so I guess I'll just recopy that and paste it so we have our notes all standardized. So that would be that. Okay. Oops, undo. All right. Okay. So what we can do then is use our model to solve questions contextually, just like we've done before, either solving for an x or solving for a y. Okay. So we have our equation, pretty standard. Again, we click log mode and we have our scatter plot. So now we are going to use the graph to solve a question. So using the equation or using our model, what's the world population in the year 2020? So again, you're either given an X or given a Y. So we're given the year 2020. So X would equal, okay, so sorry, the year is 2020. Now, X represents the number of years after 1900. So then X would equal 2020 minus 1900. And of course, you can mental math this when I'm showing the work. So X is 120. So that's very important. X equals 120, and we're solving for Y. So what we do is we go back to our graph. And in the third row, we would type in X equals 120. Okay, and we've got our point of intersection. So when X is 120, the Y value is 46.941, which represents 46.971 million people in Canada in the year 2020, based on this model. So we will snip this, that's our work, and we'll put this back into our Word document. Okay, copy that. And we'll paste that there. Just make it a bit smaller. Okay, so we want that we want that intersection point. So the intersection point is 120, comma 46.971. So our final answer would be, according to the model, red. According to the model, Canada's population would be 46.97 million in the year 2020. Okay, so we just used our regression model to solve a question, estimating what the world population would be in the year 2020. And not the world, but Canada. Whoops, that is a big typo, sorry. That's a lot small for the world. So Canada's population, I don't know why I said the world there. Okay. What's going on? Is there something missing here? Okay, so I don't know, there might be a typo or something. Using the equation would be the world population. This is Canada and it's 9.5 billion. Well, I guess we can estimate when would Canada's population hit 9.5 billion. Just make sure you make that change. Well, let's see what the model says. Clearly, if we go back to Desmos, okay, the graph is definitely going up. So now, here, the 9.5 billion people, that's the population. So y equals 9.5 billion, which would be 9,500 million. So technically then our y would equal 9,500 in the model, okay? And x would equal question mark. So we need to do then another Desmos graph. So I'm just gonna click off here, x equals 120. Now we're gonna say y equals 9,500. And so we have to zoom out. Okay, and we have our intersection. So this is a little bit unrealistic. Canada's population will not reach 9.5 billion, but this is just for an example. So we've got our intersection point. I'm just not copying the whole graph because I don't feel like scaling it. You should for assessment and all that, but just for the notes, I'm not going to. So I'll copy and paste that in there. And we have our intersection point. Okay, so then x equals 429.216. So the year will equal 1900 plus 429.216, which would equal the year 2329.216. So the answer in this case, I'll delete that. The answer then would be the following. Canada's population would hit 9.5 billion in the year, during the year, because it's 0.216, so it's about 1/5 of the way through the year 2329, so during the year 2329. That's based on the model, whether it's realistic or not, it doesn't matter. This is what the model is telling us. And so this is an example of using a Desmos model, an exponential model to solve for an x value if we were given a y value. So that summarizes the first example of doing regressions when you are given a data table. So to recap, you simply, you simply input the data into Desmos, and then you type in the regression model, click log mode, and then put the A and the B values in the right spots, the X, of course, in the exponent, and round as needed. So the next question is, what happens if we don't have a data table? What if we're just given a context, okay? And we have to then build the data table. And so there's two scenarios that come up here, and that is number one, exponential growth when the graph is increasing, and number two, exponential decay when the graph is decreasing. Again, the only thing that's going to be different here is that if it's exponential growth, that B value you would expect to be greater than 1. And if it's exponential decay, that B value would be a number between 0 and 1. The A value would represent the initial value of the situation, whether it's an initial population of rabbits or bacteria or whatever. The A value would represent the initial value, which of course is the y-intercept on the graph. Okay, so just before we get into that, this is your assignment then to work on these questions. I would ask that you do it in the notes here. You printed it off, hopefully, so you can do all the work in here, all right, to keep it all together. And that would be an important assignment to do. So you should work on that today and tomorrow. Alrighty, so I'm going to close this one off and open up the last note set, which is the one that I asked you to download today, and that is doing regressions without a data table. So I kind of gave you the intro, but again, we'll go through it. Sometimes you'll be given a scenario involving exponential growth where the B value is greater than 1, or exponential decay when the B value is between 0 and 1. You will have to determine the values of the independent, okay, so independent variable is X, and the dependent variables Y, in order to get the regression model. So X is the independent, and of course Y is the dependent variables. There's two methods we can do this. So number one, we can fill in data tables and use Desmos to get the regression equation. We recognize the initial value and the rate of change and fill those values into the equation. That would be sort of following a pattern that's based on the scenario that we're given. The second method is called the pre-calculus method. So it's a kind of a little shortcut. You actually don't need to use Desmos, and I will show it to you. It's not that hard, but it's just a different way of doing it without the technology. So I'm going to show you both ways. Okay, either way, what's very important is that when we're building our model, we need to know the initial value. Okay, we need that. We have to find that, figure that out from the question, and we need to determine the rate of change and follow the pattern accordingly. So here we go. Our first example is an example of exponential decay. So we're going to expect that the B value is between 0 and 1. So here's the scenario. A hamster is treated with medication, and the amount of medication reduces by half. So the amount of medication reduces by half, which means you divide by 2. Okay, that's what that means. If it was reduced by 1/3, you would divide by 3. If it was reduces by 1/4, you would divide by 4, and so on. If 100 every 4 hours, so the medication amount reduces every 4 hours by half. If 140 milligrams of medication is initially present in the hamster, determine the exponential regression model for this equation. For this situation. Okay. So the first thing we need to do is figure out our initial value. So if X, we have to figure out what's the independent and dependent variable. Okay. So the independent variable, IV, is time. Okay, hours. So it's time in hours. And the dependent variable is the amount of medication, which is in milligrams. So X is the time and dependent variable is the amount of medication. So the amount of time. We're going to start at 0 hours. So 0 will be our initial hours, and it's going every 4 hours. So all we needed is 3 data points. So when we do this, so we always have 3 data points. So 0, 4 hours, and 8 hours. Oops. Okay. All right. So what's the initial value at 4 hours? Sorry. What's the initial value of medication at 0 hours? 140 milligrams. That's our first data point. Now it reduces by half. So to go from after 4 hours, we go 140 and we would divide by 2. So if we divide by 2, then 140 divided by 2 is 70. And 70 divided by 2 is 35. So notice that it's going down by a half. So 140 to 70, 70 to 35. If it was going further, 12 hours, then you'd go 35 divided by 2. And so on and so on. Okay, so we have that. So we can put this into Desmos. So we're going to reset Desmos. Going to insert a data table. So our X goes 0, 4, 8, and our Y goes 140, 70, 35. Now we can't see anything, so we should scale our X-axis. So X is going, we'll make it go to 24 hours. And the Y-axis, we have to start it at 140, so we'll go 145. Okay, so there we go. We've got it scaled a bit better. We should label our X-axis. Our X-axis is time in hours, and our Y-axis is amount of medication in milligrams. Okay, so we have our 3 points. So now to get our graph, y1 tilde ab to the power of x1. And we'll make it a different color. And you can see the graph is exponential decay. Click log mode. Notice the r squared is 1. It's a perfect fit. So the a is 140 and the b is 0.84. It's less than 1, bigger than 0, exponential decay. So I will make a snip showing the graph and also showing the information. Make sure you capture the graph as well with the labels. Okay. So based on this, our A value is 140. Our B value is 0.84. It's too small. 840896. Okay, so now our model. Well, our exponential regression model, y1 tilde ab to the power of x1. So we can say that x is the time, y is the dv, so we can keep the letters the same. So we'll go y equals a, which is 140, times b, which is 0.84 to 2 decimal places, to the power of x. And that is our regression model. Which we've just done. Now, the pre-cal method. This is how it works. Our initial value is 140, and the rate of change is reduced by half every 4 hours. So reduced by half every 4 hours. So because reduced by half means divide by 2, 2 is going to be our base. If it was reduced by third, then the base would be 3. So now, this is how we plug it in. I'll give you the general template. So you would go y equals your initial value times the base, the power of x divided by the time frame. So the 4 hours is our time frame. So that would be the model. So it would be this, y equals 140 times 2 to the power of x over 4. So if we go up into Desmos here and we type that equation in, y equals 140 times 2 to the power of x divided by 4, sorry, 1/2. My apologies. So divide by 2, so the base would be 1/2. If it was reduced by a third, then it would be 1 over 3. So that should be 1 over 2 or 0.5 to the power of x over 4. And so if I click off this, you can see that the pre-cal graph is 100% fit. So that is using the pre-cal method where you keep it as the initial value multiplied, times the base, which is what the rate of change is, to the power of x over the time frame. So if it was, say it was every hour, then it would be x over 1, which would be x. If it was every 24 hours, then it would be x over 24. It all depends what the time frame is for the rate of change. You may decide, I don't like the pre-cal method. That's fine. I just wanted to show it to you, but you can see the amount of work is a lot less than using Desmos and getting the pattern, but either way is fine. Okay, the exponential growth. We'll look at the last example. So exponential growth. The population growth of bacteria is exponential. The bacteria triples. So it triples every 5 hours. There are 25 bacterial cells initially on an agar plate. What is the exponential regression for this situation? So again, we've got x and y. So x will be the time, and this is in hours. And y is going to equal the number of bacteria cells, so number of bacteria. Or number of bacterial cells, that would be the better way to label it. Okay. So we have initial value, 25. The rate of change is triple. which means you times by 3 every 5 hours. So our time frame then, our x, is going to start at 0, then go to 5, because every 5 hours, and then the third point will be 10. Our y starts at 25. It's tripling, so 25 times 3 is 75. And if we can't do our mental math, oh, the calculator is broken. So then we would just triple. So that would be 225. So we triple the y, we add 5 to the x. So we have our 3 points. We can go to Desmos, reset, add a data table, 0, 5, 10, 25, 75, 225. So we have our 3 data points. So our x, we'll go to 30 hours, and our y will go up to, say, 500. Our x-axis is time in hours, and our y-axis is number of bacterial cells. Okay, and there we go. So you see it there, and we do our regression, y1 tilde ab to the power of x1. And it keeps going to the black color. Orange. Okay, and click on log mode. 100% r squared. So we've got our model. So we can snip that. And copy paste that into our notes. Okay, so our A value is 25. Our B value is 1.24573. And we can get our equation. So our equation was y1 tilde a b to the power of x1. So our final answer then would be y equals a, which is 25, times b. Again, we don't need the 2 decimal places because 25 is a whole number. So 25 times 1.25. We're rounding. 245 rounds up to 25 here. The 4 gets rounded up. So 1.25 to the power of x. And that would be our regression equation model for example 2, using Desmos and using the pattern that we have in this scenario. Again, getting 3 data points, okay, based on the time frame going up by 5 hours and the rate of change tripling based on what the initial value was of 25. Okay, so our method 2, our pre-cal method, okay, so y equals initial value times the base, which is the rate of change, the power of x divided by the time frame. Okay. So our initial value, so y equals our initial value, 25, times the rate of change, which is tripling, 3, to the power of the x over the time frame, so every 5 hours, x over 5. So we would have y equals 25 times 3 to the power of x over 5. that would be an equivalent model, okay, to this scenario. So now let's see if this is realistic. So I'm going to hide the regression, and we'll type in the graph that we got, or the equation that we got using the pre-cal method. Y equals 25 times 3 to the power of x divided by 5. And you'll notice that is 100% match. Again, showing that there are two ways that you can get the regression equation model, like exponential model, without a data table given. Number one, using the Desmos method, where you fill in a data table with the pattern, or using the pre-cal method. Either way, that's how it works. So I wish you the best of luck working through this. So you've got these notes filled in, and you can work on the textbook the textbook homework today. There will be an exponential regression model concept check tomorrow. So check for that on the Microsoft Teams, and good luck working through this topic.